Welcome to our deep dive into AP Statistics Topic 1.9. Today, we focus on a critical skill for any data scientist: comparing distributions of a quantitative variable. By the end of this lesson, you will be able to look at two or more independent samples and explain how they differ or align in terms of their shape, center, and spread. In statistics, we don't just describe a single group. We often need to ask, is group A different from group B? To do this effectively, we use the tools we've already mastered, like histograms and boxplots, but we look at them side by side. We'll be looking for specific features, where the data is centered, how much it varies, and whether there are unusual features like gaps or outliers. Let's get started. When comparing two or more distributions, it is not enough to simply list the characteristics of each. We must use comparative language. Words like greater than, less than, or roughly the same as are essential. If you just describe group A and then describe group B without linking them, you haven't actually compared them. A great way to remember what to compare is the acronym CUSS. We compare the center, identify any unusual features like outliers or gaps, describe the shape, and evaluate the spread or variability. And never forget context. If we are comparing the heights of basketball players and soccer players, your explanation should mention heights and centimeters or inches. Data without context is just a pile of numbers. Let's look at one of the most effective tools for comparison: side-by-side box plots. These allow us to see the medians and the variability of multiple groups at once. Suppose we are comparing the lifetimes of two brands of batteries. Notice how both plots are on the same scale. This is vital. You cannot compare distributions if their axes don't match. First, let's compare the center. The vertical line inside the box represents the median. We can see that the median lifetime for brand B is greater than the median lifetime for brand A. This suggests that, on average, brand B lasts longer. Next, look at the spread using the interquartile range, or the length of the box. The box for brand B is wider than the box for brand A, which tells us that the middle 50% of lifetimes for brand B has more variability than those of brand A. Finally, look for unusual features. Brand A has an outlier on the lower end, representing a battery that failed much sooner than expected. Brand B has no shown outliers. By looking at these together, we get a much clearer picture of which battery might be more reliable. Another powerful way to compare data is by using back-to-back stem plots, or parallel histograms. Let's look at how histograms can reveal differences in shape and center. Take a look at these two classes. Even before we calculate a single number, the visual difference is striking. Class 1's distribution of exam scores is roughly symmetric and ununimodal, resembling a normal curve. However, Class 2's distribution is strongly skewed to the right. This means that while most students scored lower, there are a few students with much higher scores pulling that tail out. Comparing the centers, we can see the peak, or mode, for Class 1 is significantly higher than the peak for Class 2. In general, students in Class 1 performed better than students in Class 2. Now consider the spread. Notice that the scores in Class 2 are more spread out, ranging from 40 to 100, while Class 1 is more tightly clustered between 60 and 90. This greater variability in Class 2 tells us that student performance was much less consistent in that group compared to Class 1. Comparing these shapes gives us insight into the story behind the data. While visual comparisons are powerful, we often need the precision of summary statistics to back up our claims. Let's look at a numerical comparison of two samples of home prices in different neighborhoods. When comparing centers, we look at the mean or median. In neighborhood Y, the mean home price of $600,000 is significantly higher than the mean of $450,000 in neighborhood X. This tells us that, on average, homes in neighborhood Y are more expensive. Now, let's compare the variability using standard deviation. The standard deviation for neighborhood Y is more than double that of neighborhood X. This indicates that home prices in neighborhood Y are much more spread out from the mean, whereas prices in neighborhood X are more consistent or tightly packed around their average. By comparing these specific values, we move from saying it looks more spread out to saying it has a standard deviation that is $70,000 greater. This precision is key to a strong statistical analysis. We used box plots and histograms to compare centers, shapes, and spreads. We used mean and standard deviation to provide numerical evidence for our comparisons. We used comparative language to link multiple datasets. You are now equipped to compare distributions of quantitative variables using both visuals and numbers. Great work!